Hi everyone, today we are going to discuss 3 problems from our Math 100 discussion task, which are question 1, question 2 and question 4. This question involves set operation in the planes, divisibility proof and Pythagorean related question. Our discussion will focus on understanding the ideas behind the solution, not just the final answer. We will also share different viewpoints to make the concept clearer. We will start with question 1, then move on to question 2 and finally discuss question 4. Let's answer question 1 first.
Okay, so first question, determine the union of R in I, A, R, a set of X, Y. For every element R greater and equal to 0, such that X square plus Y square equal to R squared. So let's X, Y in R real number squared. We define R equal to square root of X squared plus Y squared greater and equal to 0. Then X squared plus Y squared equal to R squared. This means every point in R squared lies on some circle A. Therefore, union R in I, AR equal to real number squared. So for intercept R in I, AR equal to set xy equal to x squared plus y squared equal to r squared for all r equal greater than equal to 0. This means x squared plus y squared equal to 0 squared equal to 1 squared equal to 2 squared equal to 3 squared and so on. Because this is impossible because there is no number that can equal to all r. Therefore, R in I, AR equal to the empty set. So there is no can equal the number R.
The set BR. It shows the element S and Y in real in R square. And then union it asks us to determine union R in I BR and intersection R in I BR. Firstly, for the union, it shows the element X and Y, and then it shows the element R more than or equal to 0, such that X square plus Y square is less than or equal to R square. Firstly, X square plus Y square and less than or equal to R square. It shows the field this circle plus inside. For any xy, choose R square root at equal to square root x square plus y square. Then x square plus y square is less than or equal to R square. So every point belongs to some BR. Therefore, union R in I BR is equal to real number square. And then let's move to the intersection. Intersection R in I BR. The smallest as the value of R. We consider the smallest disk when R equal to 0. The only point that lies inside every disk, no matter how small, is the origin. So, x square plus y square is less than or equal to 0 is happen when we only take x equal to 0 and y equal to 0. So, the union is R square and the intersection is the set containing only 0 to 0. And let's move on to question 1C, the set CR.
Okay, so we go to next question C. So for union R in I is equal to set xy, there exists R equal and greater and equal to 0, such that x squared plus y squared greater than R. So we take starting number, which is R equal to 0. We got x squared plus y squared greater than 0, which means all number x and y except x equal to 0 and y equal to 0 is true. Therefore, we get union R in I, CR equal to real number squared, reject the set 0, 0. So for question for intercept CR, the set of xy x squared plus y squared greater than r squared for all r greater and equal to 0. But we know that r squared can be a large number and any arbitrary large number. This means no finite x squared plus y squared can be greater than all r squared. So no point satisfy this equation. Therefore, intercept r in ICR is equal to empty set of this question.
So let's go with question 2. So the result is for all natural numbers n in n, prove that n cube plus 5n is divisible by 6. So we have three methods we use in question 2. First, mathematical induction, direct proof, and contradiction. So let property Pn be n cube plus 5n is divisible by 6. So for the basis step, for n equal to 1, so we substitute n in n cube plus 5n. So we substitute the n, 1 cube plus 5 equal to 6 is divisible by 6. Let's go for the induction step. Suppose Pn is true for all natural numbers and in n natural numbers, then n plus 1 cube plus 5 times n plus 1 equal to. So we factorize and until we get n cube plus 5n plus 3n, n plus 1, 3n times n plus 1 plus 6. So by induction hypothesis, we know that n cube plus 5n is divisible by 6. So n cube plus 5n is equal 6k for some integer k. Thus, n plus 1 cube plus 5 times n plus 1 equal to 6k plus 3n squared plus 3n plus 6 is equal to 6k plus 3n times n plus 1 plus 6 is divisible by 6. Thus, Pn plus 1 is true by mathematical induction. So we know that Pn is true for all natural numbers and in n natural numbers.
For all natural numbers and element of natural number, prove that n to power of 3 plus 5n is divisible by 6. N to power of 3 plus 5n equal to n to power of 3 plus minus n plus 6n. We get n times n squared minus 1 plus 6n. The product is product of consecutive integers. In any two consecutive integer, at least one must be even. Therefore, the product n minus 1 times n plus 1 is divisible by 2. Exactly, 1 must be multiplied of 3. Therefore, the product n minus 1 time n plus 1 is divisible by 3. Since the term is divisible by both 2 and 3, the product must be divisible by 2 times 3 equal to 6. We can write this we can write this as n minus 1 times n plus 1 equal to 6k for some integer k. Substitute expression n to power of 3 plus 5n equal to 6k plus 6n equal to 6 times k plus n. For all natural number n, element of n, prove that n to the power of 3 plus 5n is divisible by 6. Assume that there exists at least one natural numbers n. Prove that n to the power of 3 plus 5n is not divisible by 6. N equal to d cube plus r, d equal to 6, 0 less than r less than 6, r equal to 0, 1, 2, 3, 4, 5, n equal to 6, n equal to 6 q plus r. We let n q to r. We let n equal to r. In case 1, r equivalent to 0, n to the power of 3 plus 5n equal 0 to the power of 3 plus 5. We go on to conclusion. Since all the remainder is 0 when divided by 6, we conclude this contradicts the assumption that there is n where the expression is not divisible by 6. The statement is true which n to the power of 3 plus 5n can divisible by 6 for all n element of n. We decide that the direct proof provides better insight for the question.
Lanjutkan
Question 4, which introduces us to Pythagorean triple. Now recall that a triple ABC of positive integers is a Pythagorean triple if a square plus b square is equal to c square. Thus, if ABC is a Pythagorean triple, then a divided by c square plus b divided by c square is equals to 1. Now for question A, the question asks us to show that if u and v are real numbers such that u square plus v square is equals to 1, then u plus v square plus u minus v square is equals to 2. Now, the first step to solving question A is we suppose that u and v are arbitrary rational numbers such that u square plus v square is equals to 1. Then, to show that, to prove the equation, we simply show that the left hand side is equals to the right hand side. So, to do this, we can simply expand u plus v square plus u minus v square. Then, during our expansion, we will notice that we will get 2 times u square plus v square. Now, if you look back at the question has given us u square plus v square is equals to 1. So, we can simply substitute 1 into our equation, and then we will get 2 times 1, which is equals to 1. So, therefore, u plus v square plus u minus v square is equals to 2. Now for question B, given that there are no rational solutions to the equation x square plus y square equals to 3, prove that there are infinitely many rational solutions to the equation x square plus y square equals to 2. Now, we need to show that x square plus y square equals to 2 have infinitely many rational solutions. To solve this question, we first need to find a rational solution that satisfies the equation. So, notice that the coordinate 1, 1 is a rational solution because 1 square plus 1 square is equals to 2. Now, we let R be any rational number. Then, by using y minus 1 equals to r times s minus 1, which is a straight line equation with r as the slope, we can rewrite it as y equals to r times s minus 1 plus 1. Then, we can use back the equation s square plus y square equals to 2 and substitute y equals to r times s minus 1 plus 1 into the equation. Then, we can do some algebra and expansion, and finally, we will get the final equation 1 plus r square s square plus negative 2r square plus 2rs plus r square minus 2r equals to 0. Now, notice that 1 plus r square times s square plus negative 2r square plus 2r times s plus r square minus 2r is in the form of a quadratic equation. This means that there are other roots that also satisfy the equation, and by doing some algebra, we can obtain these roots, which are s equals to r square minus 2r minus 1 divided by r square plus 1, and y equals to negative r square minus 2r plus 1 divided by r square plus 1. Since r is rational, then r square plus 1, r square minus 2r plus 1, and negative r square minus 2r plus 1 are also rational, and this makes s and y also rational. Since in the beginning of the question, we let r be any rational number, this means that there are infinitely many rational numbers r. Therefore, it follows that there are infinitely many solutions for the equation s square plus y square equals to 2. Lastly, for question C, it asks us how many rational solutions to the equation s square plus y square equals to 4. Now, we can start by supposing that s square plus y square equals to 4. Then we can rewrite the equation as s divided by 2 squared plus y divided by 2 squared equals to 1. Then we let u equals to s divided by 2 and v equals to y divided by 2. Then we simply substitute back u and v into the equation that we have rewrite, and we will get u square plus v square equals to 1. Now, we can simply follow back the same step in question B. We let r be any rational number. Then, we can write v equals to r times u minus 1, which is another straight line equation with r as the slope, and the coordinate 1, 0 as a rational solution to our equation. Then, to solve this, we can use u square plus v square equals to 1 and substitute in the v equation that we have obtained. So, by substituting that, we can do some algebra and expansion, and we will get the final equation 1 plus r square times u square minus 2r square u plus r square minus 1 equals to 0. Notice that 1 plus r square notice that the equation is also in the form of a quadratic equation. So, by doing some algebra, we will get the other roots for this question, which are u equals to 1 minus r squared divided by 1 plus r squared, and r equals to 2r divided by 1 plus r squared. Since r is rational, then 1 plus r squared, 1 minus r squared, and 2r are rationals. Therefore, this also makes u and v also rationals. Since there are infinitely many rational numbers r, it follows that there are also infinitely many solutions for s square plus y square equals to 4.
To conclude, question 1 helped us visualize union and intersection geometrically. Question 2 show how different proof technique can lead to the same conclusion. But among the three methods, direct proof gives the clearest insight into why the result is true, while induction is more systematic and general. And lastly, question 4 connected algebraic equation with geometric ideas and rational solutions. Overall, this problem highlights the importance of logical reasoning and mathematical structure. And lastly, that is the end of our discussion. Thank you.